Hey everybody, in this video, we are going to be going over Module 9 topics. We're going to start with adding and subtracting terms that have square roots in them. The rule is that if the square roots are the same, you just treat that square root like it's a variable. So here we have 4 times the square root of 14 minus 2 times the square root of 14. So this would just be 4 minus 2. So that would be 2 square root of 14. Then we have to see if we can simplify the square root of 14, but there isn't a perfect square that goes into it besides 1, and that's not going to change anything. So we're just going to leave it as 2 times the square root of 14. Same thing over here. We have 5 times the square root of 13 plus 4 times the square root of 13. Because these are the same, we can just add the coefficients in front of it. So 5 plus 4 is 9. So it would be 9 square root of 13. And 13 is a prime number, so it's not going to break down any further. Our next two problems that we have, they do not have the same square root. So what we have to do is we have to make them have the same square root. So let's simplify the square root of 27. So we're looking for the largest perfect square that goes into 27, and that would be 9. So we could rewrite the square root of 27 as the square root of 9 times the square root of 3. So this would be negative 4 times 3 times the square root of 3, which would be negative 12 times the square root of 3. Now we have to do the same thing with the square root of 12. So the square root of 12 would become the square root of 4 times the square root of 3. And the square root of 4 is 2. So we're looking at this new problem being negative 12 times the square root of 3 plus 2 times the square root of 3. So now that these square roots are the same, we can just add the coefficients together. So negative 12 plus 2, we would have negative 10 times the square root of 3 for our answer. Over here, same thing. We have the negative square root of 18 plus 3 times the square root of 32. So we have to simplify this. So this would be negative 1 times the square root of 9 times the square root of 2 plus 3 times the square root of 16 times the square root of 2. With 32, we're looking for the largest perfect square. My first thing why I hesitated is I knew that 4 went into it, but I was wondering if there was a larger number. So 16 goes into it as the largest perfect square that goes into it. So now this would become negative 1 times 3 times the square root of 2 plus 3 times 4 times the square root of 2, which would be negative 3 times the square root of 2 plus 12 times the square root of 2. So now negative 3 plus 12 is 9. So it would be 9 times the square root of 2. Okay? The next two problems are the exact same thing, except we have 3 terms to get to all be the same. So I have the square root of 63 plus 2 times the square root of 28 minus 15 times the square root of 7. Now, looking at this, I see the square root of 7. Now, 7 is a prime number. So that tells me that this can't be changed at all. So I have to keep that in my mind when I'm dealing with the square root of 28 and the square root of 63, because I want to be left with the square root of 7. So the square root of 7. So what times 7 is 63? That would be 9. So looking at the square root of 9 times the square root of 7, then when I get to 2 times the square root of 28, this would be 2 times, now what times 7 is 28? And that would be 4 times the square root of 7. So 2 times the square root of 4 times the square root of 7 minus 15 times the square root of 7. So now the square root of 9 is 3. So I have 3 times the square root of 7. The square root of 4 is 2. So I have 2 times the square root of 7. So this would be 3 times the square root of 7 plus 4 times the square root of 7, because 2 times 2 is 4, minus 15 times the square root of 7. Okay, now because they all have the square root of 7 in it, I can just add and subtract their coefficients, whatever it tells me to do. So 3 plus 4 is 7, then 7 minus 15, we're looking at negative 8 times the square root of 7. Same thing over here. I have the square root of 75 plus 3 times the square root of 48 minus 20 times the square root of 3. Now, here 3 is that prime number again. Right? That's not always going to be the case that you're going to have a prime number, but it helps to look for that prime number. So I have the square root of 3. We know that can't get broken down. So to help us along, we're going to know that we're going to be left with the square root of 3. So 3 goes into 75 25 times. So I have the square root of 25 times the square root of 3 plus 3 times, now 3 goes into 48 16 times. So I have 3 times the square root of 16 times the square root of 3 minus 20 times the square root of 3. So the square root of 25 is 5. So we have 5 times the square root of 3. Now 3 times the square root of 16, which is 4 times the square root of 3, minus 20 times the square root of 3. So this becomes 5 times the square root of 3 plus 12 times the square root of 3 minus 20 times the square root of 3. So now they all have the square root of 3. So I do 5 plus 12, it's 17. 17 minus 20, we're looking at negative 3 times the square root of 3. Okay, and that's how we add and subtract terms with square roots in them. Okay, the next thing we're going to deal with is we're going to deal with multiplication of square roots. Now, multiplication of square roots, you do not need to have the same square root, same number underneath the square root to combine them. Multiplication, you are just going to be multiplying. The key to this is that you have to simplify your answer at the end, okay? So we have the square root of 3 squared. So anytime we square something, we're multiplying it by itself. So this becomes the square root of 3 times the square root of 3. Okay, so if we have 2 square roots being multiplied, I can keep 1 square root and make it 3 times 3, which is 9. Now, what is the square root of 9? That would be 3. Okay, now some of you might look at the square root of 3 squared and know that a square cancels out the square root because they are inverse operations. So in this case, if that's the case, if we have a square root squared, that would cancel out and give us 3 as well. So whatever way you want to look at that, that would be fine. Okay. Here we could apply the same principle. I have the square root of 27 times the square root of 3. So I can take my calculator and I can actually figure out that the square root of 27 times 3 is 81. And the square root of 81 is 9. Okay, so I could definitely do that. Another thing you could do is you could simplify the square root of 27 and then figure that all out that way. I find it much easier to multiply and then simplify. So here I have the square root of 32 times 2 times the square root of 18. That 2, deal with that after the fact. So this becomes 2 times the square root of 32 times 18. Okay, 32 times 18 is 576. So this becomes 2 times the square root of 576. And the square root of 576, hopefully this comes out nice. It does, it's 24. So 2 times 24 would be 48 for your final answer. Okay, so we're multiplying the 2 numbers inside the square root first, evaluating the square root, then we can multiply it by the number after the fact to get 48. And that is multiplication. Okay, the next thing we're dealing with is we're dealing with division of square roots. Just like multiplication, you do not need there to be the same square roots in order to divide them. Here we have the square root of 85 divided by the square root of 5. This becomes the square root of 85 over 5. And what is 85 divided by 5? That would be the square root of 17. Now, 17 is a prime number, and I can't simplify it, right? Because no perfect square is going to go into it. So I'm going to leave my answer as the square root of 17. Okay. Here I have the square root of 3 divided by the square root of the square root of 75. So I make this the square root of 3 over 75. Now 3 can't be divided by 75, but I can simplify that fraction or reduce that fraction. So I'm going to make that the square root of 1 over 25. Now that I have the square root of 1 over 25, I can break that back up again because you can see 1 and 25 are both perfect squares. So I can make this the square root of 1 over the square root of 25. And the square root of 1 is 1, and the square root of 25 is 5. So our answer would be 1/5. So I made it one fraction. I simplified that fraction. Then I saw that both of these are perfect squares. So I broke it back up into 2 square roots. Took the square root of the numerator, got 1. Took the square root of the denominator and got 5. So my final answer would be 1/5. Okay. Here we have the square root of 54 divided by the square root of 6. So I'm going to make this the square root of 54 over 6. Okay. 54 divided by 6 is 9. So this becomes the square root of 9. And the square root of 9 is 3. And that would be that answer. That's an easy one. Okay. So that is division. Okay. Here we have introduction to simplifying a sum or difference of radical expressions univariate. So it's the same thing. We're adding and subtracting, multiplying and dividing. Actually, we're not dividing these, but if we have variables in it now, okay, same rules apply to the ones that we were dealing before. It has to have the same exact thing underneath the radical. Okay, so here I have the square root of 63x minus the square root of 28x. As you notice, these x's are not raised to an even power, so I can't do anything to take those out of the radical. But what I can do is I can simplify the square root of 63. Okay, so the square root of 63 times the square root of x. And the square root of 63 becomes the square root of 9 times the square root of 7 times the square root of x. So this would be 3. And this would be the square root of 7 times the square root of x. I'm going to put those back together underneath 1. So I have 3 times the square root of 7x. I have to try to do the same thing over here. I want to get that 7x that I had over here. That helps me with this one. So what could I pull out of 28x that's going to give me 7x? Well, I know that 4 times 28 is 7. So I can do the same thing I did over here, or I could cheat a little bit. I can make this the square root of 4 times the square root of 7x, because I know that this had to be the 7x. So the square root of 4 is 2. So I have 3 times the square root of 7x minus 2 times the square root of 7x. Now that these are the same, I can subtract them. So 3 minus 2, this would just be 1 times the square root of 7x, or just 7x. Okay, over here to the next problem. I am adding, so I need there to be the same. Okay, I need there to be the same thing underneath the radical. So I have the square root of 27z plus the square root of 75z. Here I have that z again. I have to keep that in there. So let's simplify the square root of 27. It's 27, well, I know 9 goes into it. So the square root of 9 times the square root of 3 times the square root of z. And the square root of 9 is 3. So this becomes 3 times the square root of 3z. So when I'm dealing with the square root of 75z, I want it to be left with 3z. So what can I take out of 75z to give me 3z? That would be 25. So I can make this the square root of 25 times the square root of 3z. And the square root of 25 is 5. So I have 3 times the square root of 3z plus 5 times the square root of 3z. So these are the same. So I add the coefficients. So 3 plus 5. This would be 8 times the square root of 3z for my answer. Okay. Our next problems are all multiplication. When I'm dealing with multiplication, I don't have to have like things underneath the square root. What I'm going to do is I'm going to multiply whatever's underneath the square root, create one square root, and then simplify it. So let's multiply what's underneath. So this becomes the square root of 6 times 3, which is 18. Then I have c to the 6th times c. This would really be c to the 1st. So this would be c to the 7th. So now I have to simplify this as much as I can. So I'm going to deal with the 18 separate from the c to the 7th. So I'm going to make this the square root of 18 times the square root of c to the 7, because I have to treat both of them a little bit differently. So the square root of 18, we're looking for the largest perfect square that goes into 18, and that would be 9. So I have the square root of 9 times the square root of 2. Now the square root of 9 would be 3. So I'm looking at 3 times the square root of 2. Now we're going to go over to c to the 7th. Now that we're dealing with the square root here, so there's really a 2 here. Okay. So we're looking for the largest even number that's in c to the 7. All right, so we're looking for how many times does 2 go into 7? And it goes in 3 times with 1 left over. So this would end up being c to the 3rd times the square root of c to the 1st. Okay, or another way to look at it is I can make the square root of c to the 7th. I can think of that as the square root of c to the 6th times the square root of c to the 1st. And the square root of c to the 6th is c to the 3rd, because 6 divided by 2 is 3. Okay, so now I have 3 times the square root of 2 times c to the 3rd times the square root of c. What I have to do now is I have to take everything that's not underneath the square root and write it next to each other. So 3c to the 3rd. Then everything that's underneath the square root still, write it underneath 1 square root. So this would be 2c. So I have 3c to the 3rd times the square root of 2c. Next problem, I have the square root of 10z times the square root of 2z to the 6th. So I'm going to make this the square root of 20z to the 7th. Here I go again with z to the 7th. So the square root of 20 and the square root of z to the 7th. Z to the 7th, not 7 to the 7th. The square root of 20. What is the largest perfect square that goes into 20? It's just 4. So the square root of 20 becomes the square root of 4 times the square root of 5. The square root of 4 is 2. So I have 2 times the square root of 5. Then I have the square root of z to the 7th. So same thing here. I can say, how many times does 2 go into 7 evenly? 2 goes into 7 3 times with 1 left over. So the square root of z to the 7th becomes z to the 3rd times the square root of z to the 1st. So if I write this all out together, I have 2z to the third, right? That's whatever's not underneath the radical. And then I take the square root of 5 times z to the first, or just z. So I have 2z to the third times the square root of 5z. Okay. Over here, we have the square root of 15y to the sixth times the square root of 3y to the fourth. So if I multiply these together, this would become the square root of 45y to the 10th. Okay, so I have the square root of 45, y to the 10th. So I need to look at it as the square root of 45. And then separately, I'm going to look at it as the square root of y to the 10th. So the square root of 45, we're looking for the largest number, largest perfect square that goes into 45. And that's also going to be 9. So it's going to be 9 times the square root of 5. And the square root of 9 is 3 times the square root of 5. So that takes care of the square root of 45. Now we're looking at how many times does 2 go into 10. Now 10 is an even number, so this is going to come out to a nice even number without anything, without any y's underneath the radical. So how many times does 2 go into 10? 5. With none left over, right? So we have 5 times 2 would be 10. So therefore, I don't have any y's left underneath the square root. So my final answer would be 3y to the 5th times the square root of 5. That's how I would express that. Next is I have the same exact thing, except I'm dealing with 2 variables. So I multiply them together. So this would become the square root of 20 times 5 is 100. Then x to the 6th times x squared would be x to the 8th. And then y times y to the 5th would be, or y to the 4th would be y to the 5th. Okay, so I have to look at this 3 different parts. The square root of 100, that's easy. The square root of x to the 8th, that's pretty easy too. And the square root of y to the 5th. Now 5 is an odd exponent, and I'm taking the square root of it, so I know there's going to be something left. So the square root of 100, that's 10. The square root of x to the 8th. So I want to know how many times does 2 go into 8? It goes in 4 times with none left over. Okay? So now I have the square root of y to the 5th. How many times does 2 go into 5? Well, 2 only goes into 5 2 times. So I have y squared with 1 left over. So I have the square root of y to the 1st. So when I write this, I leave all the numbers that are outside, that are not underneath the radical. I write them first. So 10x to the 4th y squared. And then I only have a y left underneath the square root. So my final answer would be 10x to the 4th y squared times the square root of y. Okay. Last problem is I have the square root of 10x squared y to the 9th times the square root of 2x squared y squared. So I'm going to multiply this all together. So I'm going to get the square root of 10 times 2, which is 20. X squared times x squared is x to the 4th. And I have y to the 9th times y squared, which is going to be y to the 11th. Okay, so I have to deal with these 3 things separately. The square root of 20, the square root of x to the 4th, and the square root of y to the 11th. Now the square root of 20, 20 isn't a perfect square, so I have to find the largest perfect square that goes into it. And that would be 4. So I have the square root of 4 times the square root of 5. The square root of 4 is 2. So this would be 2 times the square root of 5. Now I have the square root of x to the 4th. So there's a 2 here. How many times does 2 go into 4? 2 times with none left over. So that just becomes x squared. And then I have the square root of y to the 11th. How many times does 2 go into 11? It goes in 5 times with 1 left over. So I have y to the 5th times the square root of y. So now I rewrite everything that's not underneath the square root. So that would be 2x squared y to the 5th, and then everything that's underneath the square root still, which would be 5y. And so my answer would be 2x squared y to the 5th times the square root of 5y. And that is module 9.